Welcome. Get comfortable. Let your breathing slow. Tonight, we're going on a journey through time, back to the very beginning of our planet. We will explore how our world formed and how it continues to change. Allow yourself to relax. Breathe deeply. Feel your eyes getting heavy and your body getting light. Let the tension release slowly through the tips of your fingers with each breath. Breathe out as the tension melts away. And as you drift off to sleep, follow me on this astonishing journey, spanning billions of years, from clouds of cosmic dust to the living world beneath your feet, and perhaps to the very distant but eventual end of the Earth as we know it. There's no rush. We have all the time in the world. Let's begin. Before Earth existed, before the sun burned bright, the materials that would one day become our planet drifted through the darkness of space. The elements that make up Earth, the carbon in your body, the oxygen you breathe, the iron at the planet's core. All of these were forged in earlier generations of stars, ancient suns that lived and died long before our solar system was born. When those massive stars exhausted their fuel and exploded in brilliant supernovas, they scattered these elements across the galaxy. Clouds of gas and dust, enriched with the building blocks of worlds to come. About 4.5 billion years ago, give or take 100 million years, one of these clouds began to collapse. Gravity drew the particles together, slowly at first, then faster. As the cloud contracted, it began to spin, flattening into a disk. At the center, where most of the mass concentrated, temperatures and pressures rose until nuclear fusion ignited. The sun was born, but the story wasn't over. Around this newborn star swirled a rotating disk of leftover material, a solar nebula of gas and dust. And it was here, in this cosmic whirlpool, that Earth would form. Earth formed approximately 4.4 to 4.6 billion years ago, give or take a few tens of millions of years. That's a number almost too vast to comprehend. If you tried to count back 1 second at a time to Earth's beginning, you'd be counting for more than 140 years. But we have time, all the time we need. The location where Earth formed was crucial, not too close to the sun, where it would be scorched, not too far away, where everything would freeze. Earth formed in what scientists call the habitable zone, that perfect distance from the sun where liquid water could exist on the surface. This wasn't luck. It was geometry and gravity working together over millions of years. In the beginning, there was dust, tiny grains, each one microscopic, floating in the solar nebula. These grains collided gently in the swirling disk. Some stuck together. Electrostatic forces held them. Slowly, like snowflakes gathering into a snowball, these dust grains accumulated. Grain by grain, collision by collision, they grew, from dust to pebbles, from pebbles to boulders, from boulders to mountains tumbling through space. These growing bodies are called planetesimals, and they were the building blocks of planets. As some planetesimals grew larger than others, something remarkable happened. Their gravity strengthened. Now they didn't just wait for collisions. They reached out, pulling in nearby material. The bigger they got, the more they could attract. Scientists call this runaway accretion. Once a planetesimal became large enough, it grew explosively, sweeping up everything in its orbital path. The proto-Earth, still far from finished, dominated its region of the solar nebula. The young Earth grew with astonishing speed, at least on cosmic timescales. Within roughly 10 to 20 million years, Earth reached near its present size. 20 million years sounds like forever, but in the lifetime of a planet, it's the blink of an eye. During this time, Earth was hammered by impacts. Planetesimals, some as small as houses, others as large as cities, slammed into the growing world. Each impact released tremendous energy. Every collision added not just mass, but heat. Kinetic energy transformed into thermal energy. The proto-Earth grew hotter with each strike, but impacts weren't the only heat source. Deep within the growing planet, radioactive elements decayed, releasing heat from within. Gravitational compression added even more energy as material piled up and the planet's own weight squeezed its interior. The combination was overwhelming. Early Earth was not a solid, cool sphere. It was largely molten, an ocean of liquid rock. A global magma ocean covered its surface, glowing red and orange in the darkness of space. In this molten state, Earth began to organize itself. Heavier elements sank, lighter ones rose. Dense iron and nickel, responding to gravity, descended toward the center. They sank through the lighter silicate rocks, slowly at first, then in great iron rain. Over millions of years, these metals accumulated at the planet's core. Meanwhile, lighter silicate rocks, rich in silicon, oxygen, magnesium, and aluminum, floated upward, forming what would become the mantle and eventually the crust. This process, called differentiation, gave Earth its layered structure, a dense metallic core at the center, composed mostly of iron and nickel. Surrounding it, a thick mantle of silicate rock, hot and capable of slow, viscous flow. And eventually, at the surface, a thin crust of the lightest rocks. This wasn't instant. It took time. Millions of years of settling and sorting while the planet slowly cooled. The formation of the core had another crucial consequence. As iron and nickel separated from lighter elements and sank, they released enormous amounts of heat. This heat, combined with the residual warmth from Earth's formation, powered something essential, the geodynamo. Deep within the liquid outer core, flows of molten metal began to move, driven by heat and the planet's rotation. These flowing, electrically conducting metals generated a magnetic field. Earth's magnetic field, invisible but vital, formed a protective shield around the planet. It deflected the solar wind, streams of charged particles from the sun, that would otherwise strip away the atmosphere. Without this magnetic shield, Earth might have ended up like Mars. Its atmosphere gradually lost to space. But before Earth could settle into any kind of stability, catastrophe struck. Or perhaps it was the most fortunate catastrophe in our planet's history. A Mars-sized body, given the name Theia by scientists, was on a collision course with Earth. Theia had formed elsewhere in the solar system, but had drifted into an unstable orbit. The two bodies, each massive, each molten, slammed together in an impact of unimaginable violence. The collision was not head-on, but oblique, a glancing blow that was nonetheless devastating. The impact remelted much of Earth. Any crust that had begun to form vaporized. Rock became gas. The energy released was beyond comprehension. Huge amounts of material, both from Earth's outer layers and from Theia itself, were blasted into space. Some of it escaped entirely, lost to the void. but much of it remained in orbit around the battered Earth, forming a ring of debris. Over time, measured in thousands or perhaps millions of years, this ring of debris gradually came together. Gravity drew the fragments toward each other. They collided and merged, building larger and larger bodies, until finally a single large moon coalesced. The moon we see in the sky tonight, serene and silver, was born from violence and fire. The giant impact did more than create the moon. It stripped away much of Earth's original atmosphere, the gases that had been trapped during the planet's formation. Those lighter elements, hydrogen and helium, captured from the solar nebula, were blown away. The impact also affected Earth's rotation. Before the collision, Earth may have spun differently. Afterward, its rotation changed. In fact, Earth was spinning much faster than it does now. Days immediately after the moon-forming impact may have been only 6 to 10 hours long. Imagine that, sunrise to sunset in just a few hours. But the moon's gravity began to slow Earth's spin through tidal interactions. The same force that causes ocean tides today gradually transferred rotational energy from Earth to the moon's orbit. Over billions of years, Earth's rotation slowed, and the moon drifted farther away. It's still drifting, even now, moving away at about 4 centimeters per year, roughly the rate your fingernails grow. The moon did something else too, something crucial for life billions of years later. Its gravitational pull helped stabilize Earth's axial tilt, the angle at which Earth tips relative to its orbit around the Sun. Without the moon, Earth's tilt would wobble more dramatically over time, causing wild swings in climate. The moon's presence kept Earth's tilt relatively steady, creating stable seasons and a more predictable environment for life to eventually emerge. After the impact, Earth entered what scientists call the Hadean Eon, named after Hades, the ancient Greek underworld. The name suggests a hellish world, and in many ways it was. But recent evidence suggests the Hadean may have been more complex than once thought. Not just hell, but a world in transition. Earth's earliest atmosphere, the second atmosphere really, since the first was blown away, formed during and after the magma ocean phase. As the surface slowly cooled, gases dissolved in the molten rock bubbled out. Volcanic outgassing released enormous quantities of water vapor, carbon dioxide, nitrogen, methane, ammonia, and other gases. The atmosphere was dense, thick, and hot, probably more like Venus's present atmosphere than anything we know on Earth today. Surface temperatures may have exceeded 200, even 500 degrees Celsius in some places and times. Imagine standing, if you could, on the surface of Hadean Earth. You'd be surrounded by a thick, steamy atmosphere, so dense you could barely see through it. The sky would glow red with heat. As the magma ocean cooled, something strange happened. The atmosphere itself began to rain. But this wasn't water rain. Silicate material, vaporized rock, condensed out of the atmosphere and fell back to the surface in a rain of liquid rock. Slowly, over perhaps the first 1,000 years or so, this silicate rain removed the heaviest materials from the air and helped build the earliest solid crust. But the surface wasn't safe yet, not by a long shot. During the late, heavy bombardment, which lasted from about 4.1 to 3.8 billion years ago, Earth was pummeled by asteroids and comets. Some of these impacts were enormous. Large asteroid impacts from bodies tens of kilometers across repeatedly boiled the oceans and reshaped the surface. Each major impact could temporarily raise atmospheric temperatures to around 500 degrees Celsius and evaporate up to 100 meters of a global ocean. Life, if it had emerged, would have been sterilized, forced to begin again. These impacts came in waves, continuing at least until around 3.2 billion years ago. The early Earth was a violent place, constantly reshaped by bombardment from space. And yet, between the impacts, something remarkable may have been happening. Some research suggests that conditions in at least parts of the Hadean may have been cooler and more stable than once thought. Volcanic activity was intense, yes. Earth's internal heat flow was roughly 3 times higher than today, driven by 3 main sources: gravitational compression as Earth grew, radioactive decay of short-lived isotopes, and energy from frequent asteroid impacts. But this intense heating affected mainly the interior and volcanic regions. In other places, the surface may have cooled enough for temporary solid crust to form. Basaltic rock, dark and dense, solidified in low-lying areas. Some regions may have been cool enough for liquid water to exist, at least between major impacts. The picture emerging from recent research is of a Hadean Earth that was not uniformly hellish, but patchy, with some areas extremely hot and molten, while others cooled enough for oceans and crust. Water. Where did it come from? This is one of the great questions of Earth's formation. Some water was present in the original planetesimals, trapped in minerals as they formed. But most of Earth's water came later, delivered by volcanic outgassing and impacts. Volcanic outgassing from Earth's hot interior released vast amounts of water vapor, along with carbon dioxide and nitrogen. As Earth cooled, this water vapor condensed. High in the atmosphere, water molecules joined together. Droplets formed, and then, for the first time in Earth's history, it rained. It rained and rained and rained, perhaps for millions of years. The rain fell onto still hot rock, where it sizzled and evaporated, only to rise again and fall once more. But gradually, as the surface cooled, the water began to accumulate. It pooled in low-lying areas, the natural basins between volcanic highlands. The first oceans formed in these basins, probably starting as isolated seas that eventually connected into a global ocean. Asteroids delivered additional water and volatile compounds. Many asteroids, especially those that formed beyond the solar system's snowline, contained significant amounts of water locked in minerals. When they struck Earth, they released that water. Analysis of hydrogen isotopes in meteorites shows that many water-bearing asteroids have compositions matching Earth's oceans, suggesting that asteroidal impacts were a major source of our planet's water. Comets, once thought to be the main suppliers of Earth's water, now appear to have contributed only a portion of it. Most comets have isotopic signatures that don't quite match Earth's water. Current evidence favors a mixed origin, dominated by wet asteroids rather than comets. So our oceans are, in a sense, extraterrestrial, brought here from the outer solar system, one impact at a time. Some studies suggest that early Earth may have been a near water world, with little land above sea level and a global ocean covering much of the planet during parts of the Archean Eon. roughly 4.0 to 2.5 billion years ago. Because the young Earth's interior was hotter, its mantle likely stored less water than today. Heat drives water out of minerals. This would have pushed more water to the surface, creating deeper and more extensive early oceans. Imagine an Earth with almost no continents, just a few volcanic islands poking above a world-spanning sea. But even as the oceans formed, the crust beneath them was being created and destroyed. Earth's earliest crust was thin and basaltic, formed from the cooling of the magma ocean and from ongoing volcanic eruptions. This crust was not stable. It was repeatedly destroyed by impacts and by early tectonic activity. The Hadean was a time of rapid crustal recycling. Crust formed, was broken, was buried, melted, and reformed. Because of this, no intact Hadean crust survives today. The oldest large rock bodies we have, such as the Acasta gneiss in northwestern Canada, are about 4.03 billion years old. They mark the transition from the Hadean into the Archean eon. But even they have been heavily altered by heat and pressure over billions of years. However, we do have direct evidence from the Hadean, tiny but precious. Zircon crystals, durable minerals that form in cooling magma, preserve evidence of early crust and water. Zircons are remarkable. They're incredibly resistant to heat and chemical weathering. A single zircon crystal can survive the destruction of its parent rock, be eroded, transported, deposited in new sediments, and even survive metamorphism that would alter or destroy most other minerals. The most famous of these ancient zircons come from the Jack Hills of Western Australia. In metamorphosed sedimentary rocks there, geologists have found tiny zircon crystals that are 4.3 to 4.4 billion years old. 1 grain is approximately 4.404 billion years old, making it the oldest known solid material formed on Earth. These Jack Hills zircons are tiny time capsules, preserving chemical signatures from a world that no longer exists in any other form. What do they tell us? By analyzing the isotopes within these zircons, especially oxygen isotopes, scientists can infer the conditions under which they formed. The isotopic signatures show that these zircons crystallized from rocks that had interacted with liquid water at Earth's surface. This is direct evidence that liquid water existed very early, probably by 4.3 to 4.4 billion years ago, only 100 to 200 million years after Earth's formation. These zircons also contain inclusions of quartz and have hafnium and neodymium isotopic ratios, suggesting they came from felsic, silica-rich magma, the kind associated with continental crust rather than oceanic crust. This hints that some form of continental-type crust, and possibly even early plate tectonics, were already operating. Together, the Jack Hills zircons support a cool early Earth model. Rather than a long-lasting, uniformly hellish world, the Hadean may have seen solid crust, oceans, and even a hydrological cycle much earlier than once believed. This has profound implications. If Earth had liquid water and stable crust so early, could life have emerged earlier than we think? It's a tantalizing question, still unanswered. As we move from the Hadean into the Archean eon, Earth begins to take on more familiar characteristics. Plate tectonics, the process by which Earth's lithosphere is broken into moving plates, began recycling the crust. This is the mechanism that makes Earth unique among rocky planets in our solar system. The crust wasn't just sitting there, it was moving, being created at some boundaries and destroyed at others. Early continental fragments, called cratons, formed. Cratons are the ancient, stable cores of continents, made of rocks that have remained largely unchanged for billions of years. They are buoyant, made of light silicate rocks that resist being pulled back into the mantle. Over time, through volcanic activity, partial melting, and metamorphism, these cratons accumulated. They grew thicker and larger, eventually becoming the nuclei around which modern continents assembled. The mantle and crust became chemically distinct. No longer was Earth just layers of different density. Now there were distinct reservoirs of different compositions. The mantle remained dominated by iron and magnesium-rich rocks. The crust, especially the continental crust, became enriched in silicon, aluminum, sodium, and potassium. This chemical differentiation set the stage for billions of years of geological evolution. Earth's internal heat continued to drive intense volcanism. During the Archean, internal heat flow was roughly 2 to 3 times greater than today. This meant more vigorous mantle convection, more volcanism, and more rapid tectonic activity. The planet was still cooling, still settling into its long-term behavior. Subduction zones, where one plate dives beneath another, began to operate. As oceanic crust sank into the mantle, it partially melted, and the resulting magma rose to form volcanic arcs. These arcs, over time, contributed to building continental crust. Subduction and melting helped concentrate the lighter, more silica-rich materials into the continents, leaving the heavier, basaltic rocks to form ocean floor. Even diamonds, those hardest of minerals, preserve evidence of early deep Earth recycling. Diamonds form deep in the mantle, typically at depths of about 140 to 200 kilometers under old continental cratons, where pressure and temperature are extreme. They crystallize from carbon, and as they grow, they sometimes trap tiny bits of surrounding material as inclusions. These inclusions can be dated, and some diamonds contain minerals derived from oceanic crust or sediments, demonstrating that material from the surface was being carried down into the mantle by subducting plates billions of years ago. Plate tectonics, in other words, has been operating for a very long time. By about 3.2 to 3.0 billion years ago, enough buoyant continental crust had risen above sea level to create widespread land areas. This was a turning point. Land changed everything. Weathering of rocks on land, driven by rain and rivers, began to alter the chemistry of the atmosphere and oceans. Rivers carried dissolved ions and sediments to the sea. The cycle of erosion, transport, and deposition became a major part of Earth's surface processes. And then something remarkable happened. Life, which may have emerged as early as the Hadean in deep-sea hydrothermal vents or other protected environments, began to change the planet. Photosynthetic microbes, especially cyanobacteria, evolved. They could harness sunlight to split water molecules and build organic compounds, releasing oxygen as a waste product. At first, this oxygen dissolved in the oceans, where it reacted with dissolved iron, producing rust that settled to the seafloor as banded iron formations. These layers of red and black rock are found in ancient sediments worldwide, a testament to the rise of oxygen. Around 2.4 billion years ago, something shifted. the Great Oxygenation Event began. Oxygen started to accumulate in the atmosphere. This wasn't instant, it took millions of years. Initially, oxygen levels rose and fell, but gradually, persistently, oxygen built up. Sinks for oxygen, such as volcanic gases and dissolved iron, became saturated. Free oxygen began to fill the air. This was a planetary transformation. The early atmosphere had been dominated by water vapor, carbon dioxide, nitrogen, and traces of methane and ammonia, with almost no free oxygen. Now oxygen became a significant component, and with oxygen in the atmosphere came ozone. High in the atmosphere, oxygen molecules were split by ultraviolet light from the sun and recombined into ozone, a molecule of 3 oxygen atoms. Ozone absorbs ultraviolet radiation, shielding the surface. This UV shield made it possible for life to eventually colonize land and enabled more complex ecosystems to develop. The rise of oxygen had other consequences too. Methane, which had been a significant greenhouse gas in the early atmosphere, reacted with oxygen and was removed. This likely contributed to a global cooling event, and Earth may have experienced its first major glaciation, sometimes called the Huronian glaciation. Ice sheets spread across parts of the planet. The world was changing, driven now not just by geology, but by life. Over the following billions of years, oxygen levels continued to fluctuate. During the Proterozoic Eon, oxygen was present but lower than today. Then, in the late Paleozoic, particularly during the Carboniferous period around 350 to 300 million years ago, oxygen levels may have reached 30 to 35% of the atmosphere, higher than today's 21%. This high oxygen world supported giant insects and lush forests, whose remains formed the vast coal deposits we mine today. Carbon dioxide, meanwhile, varied in the opposite direction, generally declining over Earth's history as it was locked into rocks and organic matter. The atmosphere and geology entered long-term feedback cycles. Volcanic outgassing released carbon dioxide. Weathering of silicate rocks on land consumed it, as rainwater made slightly acidic by dissolved CO2 reacted with minerals. The dissolved ions were carried to the ocean, where organisms used them to build calcium carbonate shells and skeletons. When these organisms died, their shells sank and accumulated on the seafloor, eventually forming limestone and other carbonate rocks. This is how carbon was buried, removed from the atmosphere-ocean system and locked away in the crust. This carbon cycle acts as a thermostat for Earth's climate. When temperatures rise, weathering speeds up, removing more CO2 from the air and cooling the planet. When temperatures drop, weathering slows, volcanic CO2 builds up, and the planet warms. Over hundreds of millions of years, this feedback has helped keep Earth's climate within a range that allows liquid water to exist, despite the sun's gradual brightening over time. The oceans, too, underwent profound changes. Early oceans were likely rich in dissolved iron and other ions, with little or no oxygen. As oxygen rose, first in the oceans and then in the atmosphere, the chemistry of seawater changed. Oxygen allowed new forms of metabolism. It also changed which minerals could precipitate. The basic salinity of seawater, its concentration of dissolved salts, built up over billions of years as water interacted with rocks and the seafloor. Was the ocean always as salty as it is today? No. Early oceans likely started much fresher, formed mainly from water vapor outgassed from Earth's interior. As liquid water circulated through cracks in the crust and over rock surfaces, it dissolved minerals, gradually increasing salinity. Some research even suggests the very early oceans may have become more salty than today, before later processes, like the formation of thick evaporate deposits when isolated seas dried out, removed some of that salt. Modern open ocean seawater has an average salinity of about 35 grams of dissolved salts per kilogram of seawater, often written as 35 parts per thousand, or about 3.5% by weight. If you gathered all the salt from the global ocean and spread it evenly over Earth's land surface, it would form a layer many tens of meters thick. Where did this salt come from? Most ocean salt ultimately comes from two main pathways. First, weathering and runoff from land. Rainwater is slightly acidic because of dissolved carbon dioxide. It slowly dissolves minerals in rocks, releasing ions like sodium, calcium, potassium, and chloride. Rivers and groundwater carry these dissolved ions to the ocean, where some are used by organisms or locked into minerals, while others, especially sodium and chloride, tend to accumulate in solution. Second, inputs from the seafloor and Earth's interior. Seawater circulates through hot rocks at mid-ocean ridges and hydrothermal vents, where chemical reactions add some ions to the water and remove others. Underwater volcanic eruptions and outgassing also release dissolved substances, including chloride, directly into the ocean. Over geologic time, processes like the formation of thick evaporate deposits and burial of these deposits in continents have removed large amounts of salt from seawater, helping set the modern balance. Seawater's salinity has been relatively stable for hundreds of millions of years, reaching a long-term, steady state where additions roughly equal removals. As oxygen levels in the oceans rose, they did so unevenly. The deep oceans stayed low in oxygen for a long time, even after the atmosphere became oxygen-rich. Then, in the late Paleozoic, around 400 million years ago, there was another major jump in marine oxygen. These changes in oxygen and acidity controlled which organisms could make shells, how big animals could get, and where they could live. During the Cambrian period, about 541 to 485 million years ago, warmer climates, more oxygen, and lots of shallow seas helped trigger what scientists call the Cambrian explosion, a relatively rapid diversification when many major animal groups first appeared in the oceans. Hard shells, complex eyes, predators, and prey all emerged in what seems, geologically speaking, like the blink of an eye. Later, in the Jurassic, around 170 million years ago, the rise of calcium carbonate secreting plankton smoothed out ocean chemistry by depositing vast chalky sediments on the seafloor. That chemical buffering made it easier for many different shell-forming organisms to evolve and diversify, driving a major expansion of marine life. But the history of life in the oceans hasn't been smooth. Changes in ocean temperature, circulation, and chemistry have triggered several mass extinctions in marine life. Large swings in sea level and oxygen, plus volcanic activity, wiped out huge fractions of marine species at certain boundaries. The end Permian extinction, about 252 million years ago, was the worst, eliminating perhaps 90% of marine species. The end Cretaceous extinction, 66 million years ago, famous for ending the age of dinosaurs, also devastated marine ecosystems. When shallow seas flooded continents, they created wide, warm platforms, ideal for reefs and diverse marine ecosystems. When seas retreated, many coastal and shelf habitats vanished. Each extinction cleared ecological space that surviving groups could then refill in new ways. Ocean and life endlessly influencing each other. And what about the continents themselves? They were not fixed. Over deep time, the crust has been recycled many times. Ocean floor is created at mid-ocean ridges, moves away, and is eventually pushed back into the mantle at subduction zones. Continents have collided to raise huge mountain ranges, then been worn down by weathering, rivers, glaciers, and wind. Sediment is carried to the oceans and forms new rocks. Sea level has repeatedly risen and fallen. Massive volcanic eruptions and asteroid impacts have occasionally reshaped regions very quickly, compared with the usual slow pace of erosion and plate motion. Continents drift, carried on tectonic plates. They collide, merge, and break apart in vast cycles. About 335 million years ago, the continents collided to form a supercontinent called Pangaea. Pangaea, or Pangaea, was a single enormous landmass surrounded by a global ocean called Panthalassa. Almost all of Earth's land was joined together. How did Pangaea form? Before Pangaea, earlier continents and smaller landmasses drifted on moving plates and gradually converged. Over tens of millions of years, repeated collisions stitched these pieces together, closing older oceans and building major mountain belts, like the Appalachians in North America and their equivalents in Europe and Africa. This process of continental collision and suturing is a normal outcome of plate motions driven by convection in the mantle. But Pangaea didn't last. Mantle convection that helped assemble it eventually pulled it apart. Heat from Earth's interior caused upwelling beneath parts of the supercontinent, stretching and thinning the crust until new rift valleys and then new oceans formed. The early Atlantic Ocean began as a rift running north-south through Pangaea. As this rift widened, the single landmass split into several large plates that drifted away from each other, producing the present-day arrangement of continents. And they're still moving. Right now, as you rest here, continents are drifting at a few centimeters per year, about as fast as your fingernails grow. Typical speeds range from about 1 to 10 centimeters per year, depending on the plate. The Pacific plate moves northwest at about 7 to 10 centimeters per year. The North American plate moves generally west-southwest at around 1 to 3 centimeters per year. The Eurasian plate creeps eastward or southeastward at about 1 centimeter per year or less. The African plate moves mostly northeast at around 2 to 3 centimeters per year. The Australian plate is relatively fast, moving north or northeast at about 6 to 7 centimeters per year. And the South American plate is moving generally westward at about 2 to 3 centimeters per year. These motions are creating the geography of the future. The Atlantic is widening as North and South America move away from Europe and Africa at the mid-Atlantic ridge. The Pacific is shrinking in some places as the Pacific plate moves northwest and subducts under surrounding plates, creating the Ring of Fire with its earthquakes and volcanoes. India is still moving north-northeast into Eurasia, continuing to build the Himalayas. Africa is drifting northward toward Europe, contributing to mountain building in the Alps and around the Mediterranean. When might continents collide again to form another supercontinent? Models suggest that on the order of 200 to 300 million years from now, the continents could reconverge into a new supercontinent. Different simulations show different possibilities, some with the Atlantic closing, others with the Pacific closing first. Scientists have given these hypothetical future supercontinents names like Amasia or Pangaea Proxima. But this is a process unfolding over hundreds of millions of years, not a human timescale event. What causes continents to move? The underlying driver is mantle convection, plus gravity-related forces. Heat from Earth's interior causes slow circulation of solid but deformable rock in the mantle. Rising hot mantle and sinking cooler mantle drag plates along at the surface. The most important force is slab pull. As dense, cold, oceanic lithosphere sinks into the mantle at subduction zones, it pulls the rest of the plate behind it. Plates with long subduction zones, like the Pacific, tend to move fastest. At mid-ocean ridges, newly formed, hot, elevated crust tends to slide downhill under gravity, pushing plates away from the ridge. Friction at plate boundaries, the strength of the plate itself, and variations in mantle structure all modify speeds and directions. So yes, continents are still moving. They will collide again. New mountain ranges will rise. And eventually, hundreds of millions of years from now, the continents may again merge into a single landmass. Were all modern continents in Pangaea? Yes. Reconstructions show that the major present-day continents, Africa, South America, North America, Europe, Asia, Antarctica, India, and Australia, were all joined together within the supercontinent. They weren't separate continents as we name them now, but the crust that makes them up was physically connected as part of Pangaea's two big halves, Laurasia in the north and Gondwana in the south. But there are exceptions. Small pieces of continental crust, called microcontinents, probably sat outside the main Pangaean block, or were already detached when Pangaea was at its peak. Geologists have identified fragments of earlier continents that split off long before or along the margins of Pangaea. Examples include Zealandia, a mostly submerged continent that broke away from Gondwana, the southern part of Pangaea, about 80 million years ago. Zealandia now lies largely under the southwest Pacific, with only New Zealand and a few small islands above water. Another example is Mauritia, a proposed ancient microcontinent inferred from old zircons, preserved in volcanic sands near Mauritius. Mauritia is thought to have been trapped and later broken apart during older supercontinent cycles, not just during Pangaea. Then there's Argoland, whose pieces are now found scattered in mountain belts around Southeast Asia and near Australia, rather than forming a large, coherent block in classic Pangaea maps. These pieces may have been on the fringes of Pangaea, in narrow oceans, or already moving away as Pangaea assembled and broke apart. They are geologically unusual. They preserve crust that records older supercontinents, like Rodinia, and complex breakup histories different from the main Pangaea fragments. Because many are now submerged or scattered in mountain belts, they hold rock types, fossils, and histories that don't neatly match the standard Pangea to today's story. So they're not special new worlds, but they are relatively rare fragments whose positions and histories are more complicated and distinctive compared with the big, well-known continents. Volcanic activity has been a constant presence throughout Earth's history. It's driven by Earth's internal heat and plate tectonics, and it continually builds, reshapes, and fertilizes the planet's surface. Volcanoes occur where rock in the mantle or lower crust melts to form magma, and that magma can rise to the surface. There are several main settings for volcanic activity. At subduction zones, where an oceanic plate sinks beneath another plate, water and other fluids released from the descending slab lower the melting point of the overlying mantle, generating magma that feeds volcanic arcs like the Andes and the Cascades. At mid-ocean ridges, where plates pull apart, pressure drops in the upwelling mantle, causing decompression, melting, and producing basaltic magma that builds new oceanic crust. Iceland and the mid-Atlantic ridge are examples that reach the surface. In continental rifts, when continents stretch and thin, hot mantle can rise and partially melt, forming rift-related volcanoes like those in the East African Rift. And at hotspots, narrow upwellings of unusually hot mantle can melt through a plate's interior, creating chains of volcanoes as the plate moves over the plume. Hawaii and Yellowstone are classic examples. Volcanic activity reshapes Earth in many ways. Mid-ocean ridge volcanism continuously creates new oceanic crust. Island arcs and hotspot chains can grow into islands and even small continents over time. Large lava plateaus, called flood basalts, can cover huge regions with new rock. Volcanic arcs above subduction zones are where recycled oceanic crust and sediments are partly melted and turned into new, more silica-rich continental crust. Repeated intrusions and eruptions thicken crust and build mountain belts. Volcanoes also release water vapor, carbon dioxide, sulfur gases, and other volatiles, contributing to the long-term supply of greenhouse gases and the atmosphere. Big explosive eruptions can inject ash and sulfur into the stratosphere, reflecting sunlight and temporarily cooling the climate for years to a decade or so. Over millions of years, volcanic CO2 outgassing is one side of the carbon thermostat that also involves rock weathering and carbonate burial. Fresh volcanic rocks weather into mineral-rich soils that are often very fertile. One reason many people live near volcanoes. Yes, most of Earth's active volcanoes are actually under the oceans. Scientists estimate that 70 to 80% of volcanic eruptions on Earth happen on the seafloor, mainly along mid-ocean ridges and at some subduction zones and hotspots. These submarine volcanoes erupt magma onto the ocean floor, where the lava cools quickly into forms like pillow lava and builds up seamounts and ridges. Submarine volcanoes form islands when repeated eruptions pile up enough solid rock to rise above sea level. Magma rises where plates diverge, converge, or above a hotspot. Each eruption adds a layer of solidified lava, slowly building a volcanic mountain, a seamount. Over many thousands to millions of years, continued eruptions stack lava flows until the top of the seamount reaches shallow water. Once it finally breaks the surface, it becomes a volcanic island. The Surtsey eruption from 1963 to 1967 off Iceland is a classic example. A submarine volcano emerged from a depth of 130 meters, growing through explosive activity and lava flows to form an island reaching 2.5 square kilometers. It's now a UNESCO World Heritage Site, slightly smaller after erosion, at about 1.5 square kilometers. Hunga Tonga, Hunga Ha'apai in Tonga, formed from eruptions in 2014 to 2015, linking two existing islets and reaching 3 to 5 square kilometers, before much of it collapsed in the massive 2022 eruption. Niijima, in Japan, was born from an underwater volcano southeast of Iwo Jima in late October 2023, and continues to grow, initially about 500 meters long, with ongoing eruptions. Above hotspots, magma keeps rising in roughly the same place while the tectonic plate moves over it. This creates a chain of volcanic islands and seamounts that get older, with distance from the active hotspot. The Hawaiian Islands are the textbook case. Active underwater volcanoes are very common, and when they erupt enough material over long periods, they can literally build new islands out of the ocean. Throughout Earth's history, volcanic activity has been closely tied to tectonic processes and climate. Large igneous provinces, huge outpourings of lava that can cover areas the size of continents, have occasionally occurred. The Deccan traps in India, the Siberian traps in Russia, these were episodes of massive volcanism that released enormous amounts of gas and probably contributed to mass extinctions and climate shifts. The timing of such events is often linked to mantle plumes, where abnormally hot rock rises from deep in the mantle, breaks through the lithosphere, and floods the surface with lava. Earth is still changing all the time, from the deep interior to the atmosphere. Scientists track those changes with instruments on the ground, in the ocean, and in space. Tectonic plates keep moving a few centimeters per year, building mountains, widening oceans in some places, and closing them in others. Earth's crust is continually reshaped by earthquakes, volcanoes, landslides, and erosion by rivers, glaciers, wind, and waves. Ice sheets and glaciers are losing mass overall, contributing to rising sea level. The oceans are warming, becoming slightly more acidic, and their circulation patterns are shifting. The atmosphere is changing rapidly because of human-released greenhouse gases, altering temperature, rainfall patterns, and the frequency of heat waves, droughts, and extreme storms. How do scientists measure these changes? They combine many kinds of measurements. Satellites track ice loss, sea level change, land motion, vegetation, and temperature. Gravity-measuring satellite missions detect changes in water and ice mass. GPS stations measure millimeter-scale plate motions and uplift or subsidence. Seismometers record earthquakes and reveal how the interior is deforming. Argo floats, buoys, and research ships measure temperature, salinity, currents, and chemistry throughout the oceans. Laser scanning, radar, and repeat photography map changes in coastlines, glaciers, forests, and built environments. Climate and Earth system models, checked against observations, are used to understand present changes and project future ones. Different processes matter on different timescales. Over the next decades to centuries, ongoing warming from greenhouse gases will drive stronger heat waves, shifting rainfall, and more frequent extreme weather. Sea level rise from melting ice and thermal expansion of seawater will increase coastal flooding and erosion. Changes in freshwater availability will occur as precipitation patterns and snowpack change. Ecosystems will shift on land and in the ocean, affecting food webs, fisheries, and agriculture. Over centuries to many thousands of years, ice sheets will continue to respond. If large parts of Greenland and Antarctica destabilize, they could raise sea level by many meters. Long-term climate feedbacks, such as changes in ice cover and vegetation, can lock in new climate states. And at any time, though unpredictable, rare but sudden events can occur. Large earthquakes and tsunamis affecting specific regions, major volcanic eruptions that can temporarily cool the climate and disrupt air travel and agriculture. Very large super-eruptions or big asteroid impacts are extremely rare on human timescales, but would be globally disruptive if they occurred. Looking further ahead, predictions blend models, paleoclimate data from ice cores and sediments, satellite observations, and astrophysics. In about 100 million years, models suggest the continents will reassemble into a new supercontinent, perhaps called Pangaea, Ultima, or Amasia. This will raise mountains and alter climate as silicate weathering draws down CO2. In about 1 billion years, a runaway greenhouse effect may become possible as the sun brightens by roughly 10%. This increased solar energy could evaporate the oceans and sterilize the surface, ending Earth's habitability. And in roughly 5 billion years, the sun will exhaust the hydrogen in its core and begin fusing helium. It will expand into a red giant, growing large enough to engulf Mercury and Venus, and possibly Earth. Even if Earth isn't completely swallowed, the intense heat will boil away the oceans, strip the atmosphere, and leave behind a charred, lifeless husk. Tidal interactions with the expanding sun may cause Earth to spiral inward even earlier. Earth won't be destroyed by internal processes alone. Tectonics, erosion, and volcanism will keep reshaping it for as long as it exists. But the sun's evolution sets the ultimate limit. In about 1 billion years, the surface becomes uninhabitable. In about 5 to 7 billion years, the sun's red giant phase ends Earth as we know it. But that is so far in the future as to be almost unimaginable. For now, Earth endures, a blue marble in the darkness, a world shaped by fire and water, by impacts and erosion, by life and geology intertwined, from dust to planet, from magma ocean to living world. 4.5 billion years of history, written in rocks and minerals, in the curves of continents and the depths of oceans. And you are part of that story. The atoms in your body were forged in stars. The water you drink fell as rain on ancient seas. The ground beneath you is recycled crust, reshaped again and again. You are made of Earth, and Earth is made of the cosmos. Rest now. Let the weight of deep time settle around you. Billions of years compressed into these hours, from the solar nebula to the present day, from chaos to order to life. The story of how the Earth formed, the story of home. Breathe slowly. There is no rush. We've traveled through time together, and time is all we have. The Earth spins on, plates drifting, volcanoes breathing, oceans swelling and receding. A living planet, ever changing, yet enduring. Sleep well and sweet dreams.